Okay, so it's time for my law of sines proof, which should be a lot easier than my SSS similarity one, and so I'm hoping that it's a lot easier for you to both understand and actually implement. And due to that, we're going to start out more conceptual and then dive into the nitty-gritty math, and I'm just hoping this is all going to make sense to you, or at least, I mean, it should make sense to you, but then it's also a lot easier for it to make sense to you than my other proof. So let's get into it. So starting conceptually, what we're doing is we're saying that sine of A over A is equal to sine of B over B is equal to sine of C over C, which is the law of sines, and this is in terms of non-right triangles. And imagine that the triangle is drawn with a side A, B, C with angles A, B, C, and angle A is opposite side A, angle B is opposite side B, angle C is opposite side. So pretty much how we're going to do this is we're going to split the non-right triangle in half with an altitude, a perpendicular altitude, one might note. That's kind of important, just saying, to make some right triangles so we can mess around with this. And then we're going to use pretty much the definition of sine and show how on both sides the sine is equal to the same thing, because you can move around the equations to do that. And then we're going to use the transitive property a bunch and compare it so that it's all equal to each other. And honestly, it's pretty simple concept, so I don't feel that I have a lot more to say about it. I think it's going to make sense as we get into the more nitty-gritty side of things. So yeah, conceptually, we're just trying to prove that law of sines is a thing in a non-right triangle. Yeah, and then we're using right triangles to do that, of course, because right triangles can be very helpful in terms of sine, cosine, and tangent, trigonometry. Let's get into that. So, pretty much we're going to do the same process twice, just each of them are going to have different perpendicular altitudes. So I'm going to start and then go through the full thing really nitty-gritty on one side, and then kind of just like quickly go through it the second time, and then show you how those two things combine. And note that like in my flowchart proof, it looks like we're doing this all simultaneously because they're all separate things that then conjoin into one thing. So it's pretty cool. I'm going to start with an altitude coming down from angle B to side B, and this line segment altitude, whatever you want to call it, is perpendicular to side B because of the perpendicular postulate, which pretty much says that on like a given line, there's one point that's perpendicular from a point, yada, yada, yada. See the two right triangles formed? We're going to take angle A, we're going to take angle C, and we're going to find the sines of both. So according to the definition of sine is how I'm going to determine this and use as my evidence, but there are other things according to Tom, so I'm just saying what Tom wants. So sine, we know SOHCAHTOA, is opposite over hypotenuse. So we're going to take E and put that over C, and we know that's equal to sine A, and we're going to do the same thing with sine C, so E over A. So then the next thing we're going to do is we're going to use the multiplication property of equality for both and multiply sine A equals E over C by C, so that the E is like isolated on one side of the equation. So E equals C sine A of A. Then we're going to do the same thing on the other side, but with A and sine of C. So sine C equals E over A. Take that A, multiply it, and now it is E equals A sine C. Wow, magic, they both equal E. So what can we do? Transitive property. Take the transitive property and set them equal to each other. So C sine A equal to A sine C. Wow, magic. Next step, we're going to use the division property to start to form that law of sines and say C sine A over A is equal to sine of C. And then we're going to do that again with the other side and make it sine of A over A is equal to sine of C over C. Again, using the division property of equality. And pretty much that's the first thing we wanted to do anyway, so we're in a great place. Now we're going to do that on the other side. Take the definition of sine, a new altitude we've drawn. We can say that sine of B is equal to D over C due to SOHCAHTOA / definition of sine. Then we are going to take sine of C is equal to D over B. And now we're figuring out that, again, so that later we can transitive property them to look at this in the big picture sense. So now we can say D is equal to C sine of B because we multiply both sides by C using the multiplication property of equality. Do that with the other one and make it D equals B sine of C because we multiply B on both sides using the multiplication property of equality. Next step, we are going to use the transitive property since they are both equal to D and say C sine of B is equal to B sine of C. Wow. I love it how the letters are flipped. It just entertains me. Okay, I'm a math nerd. I can admit it. Next, we're going to divide both sides by B. So we've got C sine of B is over B is equal to sine of C. Then we're going to do that again, divide both sides by C and get sine of B over B equals sine of C over C using the division property of equality. And then we can combine the two things we found. So sine of A over A is equal to sine of C over C, and sine of B over B is equal to sine of C over C. We can use the transitive property to say that sine of A over A is equal to sine of B over B, and then take all those three things and we can end up using kind of like the transitive property, kind of just mushing them all together. But I'd say the real evidence is the transitive property. And we can say that sine of A over A is equal to sine of B over B is equal to sine of C over C. So this proof, the hardest part about this proof is figuring out where to draw the altitudes and just looking at the general concept. But once you have your altitudes drawn and once you're understanding the concept and what you need to do, it's really simple. So I'm really hoping that your understanding is feeling pretty solid. Again, it was pretty much just setting up our quote-unquote equation, our theorem or proof for algebra, and then doing the algebra and then using the transitive property to take all that math together. So yeah, I feel like this is a good thing to have in your little toolbox, which could be physical or metaphorical, dependent on your teacher. But it's really important to understand how these things work, and I think that understanding the law of sines is very helpful, especially for later trigonometry. So I hope that you've come away from this with a better understanding, and I hope that you enjoyed watching this video.